Hello and welcome back to this third and last part of Lecture 6. In this one, we will take a look at the modeling of chemical evolution in galaxies. Stars and galaxies are by far the most important factory of elements heavier than hydrogen and helium, the elements that we astronomers all call metals. And so once these have formed inside these stars and the stars reach the end of their life cycle, this gas is recycled into the ISM, where it mixes with the rest of the ISM, enriches it, and leads to increased metallicity of that ISM, which in turn then will be ready to take part in the next cycle of star formation, form the next generation of stars, and so on. Lighter metals such as oxygen, silicon, magnesium, and alpha elements, which we will take a look at later, these form faster and earlier in the life cycle of stars, whereas heavier elements such as iron form much slower. This means, of course, that different elements are produced in different timescales, meaning that the relative abundances of these elements can be used as a method to determine the age and other properties of a stellar population. Once the first and most massive stars reach the end of their life cycle, we get to a period of a lot of core collapse supernovae. These supernovae release a large amount of mainly alpha elements into the ISM, at timescales from about 10 to about 100 million years or megayears after the formation of the stellar population. At a later point, the so-called AGB stars, asymptotic giant branch stars, will start producing larger amounts of carbon and nitrogen. But these elements will also mix into the ISM, but at a much slower rate than the elements that are produced by core collapse supernovae. Why is this? Think a little bit about that, and we will discuss that when we meet in person. Finally, type 1a supernovae and other rarer objects are responsible for producing some of the very heaviest elements, including iron, but also heavier than that. But this happens at much later times, at timescales from about 1 gigayear and onwards. One of the most simple models for the buildup of heavy elements is what we call the one-zone instantaneous recycling model. The enrichment, the chemical enrichment of the ISM is very complex and very complicated if we want to get every little detail right. So in order to quantitatively think about this and to make any kind of computations and predictions, we do need to make some kind of simplifying assumptions about it. And one such model is the one-zone instantaneous recycling model. So as you can see from the name, this one contains two major assumptions. The first one is that there's one zone in the gas, which means that all the gas that we're looking at has one temperature, one density, and one metallicity. We're not talking about a gas with varying metallicity or varying properties in other ways. And the second assumption is that of instantaneous recycling. What does this mean? Well, it means that once gas has been released from stars, it is immediately ready to form new stars and be processed again, and so on. And at the same time that the processing inside the stars takes zero time. And this leads to this model that we can see here, which is also seen as equation 8.113 in the book, where you can also see the derivation of this model. This shows first, let us take a look on the left side of the equation that shows that the gas mass times the rate of change of metallicity per rate of change of gas mass is equal to this letter P, which is the yield of metal production in the stars. This number will be generally increasing the metallicity. The next thing we have here is the metallicity difference between the gas and stars in this system and accreted material, because we're looking at a galaxy that is in contact with its environment, in contact with its surroundings, and it can accrete pristine gas from the intergalactic medium. And this pristine gas will, of course, fall down onto the galaxy. It will mix with the existing ISM in the galaxy, and it will be decreasing the metallicity, usually. We could devise a scenario in which this accreting gas was actually of higher metallicity than the one in the galaxy, the ISM in the galaxy, but this doesn't really happen in practice. So this would be kind of a contrived example. And finally, we have this quantity here, which is the accretion rate of external media or of IgM media onto the galaxy. And here, this number R, which you see actual formula for here, is called the total return fraction of the gas. So this is the fraction of gas that is returned back to the IgM. So with these simplifications, the modeling of stellar or chemical evolution becomes more manageable, but it is still not easy. Can you see? No, you cannot see. But it is still not easy. So we can make an even more simplifying assumptions, and that one is what we call the closed box model. So this closed box model, on top of the one zone instantaneous recycling model that we had before, also assumes that this gas is now in a closed box. There's no material exchange with the surroundings, and there is therefore no accretion from the IgM and so on. In this case, under these assumptions, we have that the average metallicity will over time approach the net stellar yield, the total yield over time. This is not a very realistic model, but it is one that is good for studying, and it's one that is good for using a kind of as a toy model to understand the way that these chemical evolution models work before one moves on to more realistic but also more complicated models. This closed box model, I should say, is a very important model that we will spend more time on in the future in exercises and so on. That was it for today's lecture, lecture 6. Here are the day's discussion questions, which I would like you to think about until we meet. The first question is question A, and it says, discuss the star formation main sequence. Why do you think galaxies lie on it, and what affects the slope of the star-forming main sequence? Question B says, the closed box model of the buildup of heavy elements has one big drawback. It does not really match the observation of galaxies. Discuss the assumption that is made in this model and how they could cause problems for the realism of this model. That was it for today. Thank you for staying with me, and I will be looking forward to seeing you in the next one. Bye for now.